Okay, Calculus 3 students, hi again, this is Mr. Lewitt. I know I said I wasn't going to make another video for about a week, but, well, I changed my mind. So, a couple of things. There's a lot of stuff I want to cover in this video, and I don't want this video to become unbelievably long. So please keep up with me. We're going to go at a fast pace. Okay, I don't want this to become a 2-hour or 3-hour lecture. So let's move kind of fast. So there is an algorithm that I think is really important for you guys to understand and to understand how to use. It is called Gaussian Elimination, or Gauss-Jordan elimination. Okay, so the algorithm goes by two different names. Some people call it Gaussian elimination. Some people call it Gauss-Jordan elimination. Some of you may already know how to do this. So strictly speaking, technically, this is not part of Calculus 3. Students usually learn this in pre-calculus or college algebra or finite math, or sometimes the first semester of linear algebra. However, I feel that by the time you leave Calculus 3, you have to know this algorithm. So if you don't know this algorithm, if you don't know how to do this, if you don't know how to use this mathematical method or mathematical recipe, please watch this video very carefully, because this is something you really should know how to do. There are some Mathematica tricks and shortcuts that can help you with this, but still, you should understand the logic of this algorithm, because it's actually a very important algorithm. And even if you do know the algorithm, I strongly encourage you to watch the rest of the video. Okay? So I'm going to pick 3 random numbers. 3 random numbers. X is going to be a random integer between 0 and 1,000. And I don't know what, I don't want to know what X is. I don't want to know what X is. So to suppress output in Mathematica, I'm going to end my command with a semicolon. Shift Enter. Because I don't want to know what X is, not yet. Y is equal to random integer. Let's pick another random integer in the range 0 to 1,000. And I'm going to suppress the output because I don't want to know the value of y. And then z is going to be another random integer in the range 0 to 1,000. But I don't want to know what z is. Okay, Shift Enter. Okay, so now I'm going to make up some equations. How about x plus y plus z, x plus y plus z, Shift Enter. 2,113. Okay, what about 2x? Well, here's another one. Here, you know what? Instead of x plus y plus z, well, we could do that too. Okay, we'll leave that as it is. I'm trying to think of something a little more complicated, but that's okay. Let's keep it simple. X plus y plus z is 2,113. And what about 2x plus 3z? That's going to be equal to 3,704. And then what about y minus z? That's going to be negative 109. So based on these three equations, how could I figure out the values of x and y and z? Okay, how could I figure out the values of x and y and z? So I'm going to build a matrix, and I'm going to call it matrix A. In linear algebra, they love to call matrices, they love to give the name capital A to matrices, capital A, capital B. In Mathematica, you're not allowed to use capital C as a name, or capital D, by the way, but you can use capital A or capital B to name a matrix or any variable or function of your choosing. Okay, so let's get started. Look at the first equation. What are the coefficients of x and y and z? Well, I have one x, I have one y, I have one z, and the sum is 2,113. What about the next row? The coefficient of x is 2, there's no y, so the coefficient of y is 0, and the coefficient of z is 3. And the sum is 3,704. And then finally, look at the last equation, y minus z. There is no x. The coefficient of y is 1. The coefficient of z is negative 1. And the sum is negative 109. Okay, so what I have to do now is simplify the matrix. And by the way, the order of the equations really doesn't make a difference. Not really. Okay, I could switch the first and third equations, and really I would still get the same solution. So how would I do that? I want to switch the first and third equations. So how would I do that? Okay, so as you can see, I switched the first and third equations. Okay, not a big deal. I could switch the first and second equations, and I'm still going to get the same answer. So let's see, I'm going to switch the first and second equations. Okay, terrific. So now, how do I begin this process? How do I begin the process of Gauss-Jordan elimination or Gaussian elimination? So first I have to begin working on the first column, and then the second column, and finally the third column. Okay, I have to work on transforming these columns. So the 2 over here has to be changed into a 1, and all the other numbers are going to be replaced with zeros. And then I want a 1 over here in the second position. Okay, second row, second column. That has to be a 1. And these numbers will be changed into zeros. And then in the third row, third column, this number has to be a 1, and then these numbers have to be zeros. Okay, so let's begin working by transforming this 2. How do I change it into a 1? I'm going to multiply the first row by 1/2. Why? Because 1/2 times 2 is 1. So I'm transforming the first row by multiplying every number in the first row by 1/2. Okay. What about this? What about this? There's a 1 here. I want that to be a 0. So what I'm going to do is, okay, I see there's a 1 here, as there should be. Right over here, there's a 1. This should be 0. Well, 1 minus 1 is 0. So every number in the third row, okay, every number in the third row minus the corresponding number in the first row. Okay, so far so good. So the first column is finished. The first column is finished. Now I have to look at the second column. Well, there's a 1 here in the second row, second column, and that's good. Okay, there has to be a 0 here, and there should be a 0 right here below that 1. So in each column, you're going to have 1, 1, and all the other entries are going to be 0. So first row, first column, a 1. Second row, second column, a 1. Third row, third column, a 1. Okay, so let's try it again. So we're going to have to change the third row. Every number in the third row, and let's see, I'm going to subtract from every number in the third row the corresponding number in the second row. Okay, the first two columns are finished. The first two columns are in canonical form. The first two columns of my matrix are in canonical form. Okay. Or I could write a comment to myself in Mathematica by using these delimiters. The first two columns of my matrix are in canonical form. Okay. So now I need to begin working on the third column. I begin by creating the canonical 1. There's a 1/2 here. That number should be 1. How do I change 1/2 into 1? I multiply by 2, the reciprocal of 1/2. So A3 is equal to 2 times A3. The third row of A is equal to 2 times the third row of A. So I'm updating every number in the third row of A. 2 times 0, 2 times 0, 2 times 1/2, 2 times 370, which will be 740, I believe. Okay. So now I need to replace the -1 with 0. How should I do that? Well, refer back to my canonical 1. 1 plus -1 is equal to 0. So I'm transforming the second row by taking each number in the second row and adding to it the corresponding number in the third row. Okay. So now I'm doing the same thing basically to the first row. There's a 3/2 here, but that number should be 0. That number should be 0. So how will I accomplish that transformation? I'm going to take every number in the first row minus 3/2 every number in the corresponding. Let me say that again. I'm going to take every number in the first row and subtract from that number 3/2 times the corresponding number in the third row. So let me say that carefully one more time. I'm going to take every number in the first row and subtract from that number 3/2 times the corresponding number in the third row. So I'm transforming the first row minus 3/2. And why am I doing minus 3/2? Because 3/2 minus 3/2 times 1 is equal to 0. 3 halves minus 3 halves times 1 is equal to 0. Excuse me. So why did I choose? Well, this looks great. This looks perfect, okay? This looks perfect. So I'm taking every number in the first row and subtracting from it 3 halves times the corresponding number in the third row. The third row. Okay? And that's going to produce the new first row. So according to my matrix here, x is equal to 742, y is equal to 631, z should be equal to 740. Okay, is that true? What is x? X really is 742. What is y? Y really is 631. What is z? Z really is 740. Okay, and if you look at these equations here, it makes perfect sense. So what was my first equation? My first equation was x plus y plus z is really 2,113. Why? Because 742 plus 631 plus 740 is really 2,113. So, I mean, it makes perfect sense. Okay, now Mathematica does have a shortcut. Mathematica does have a shortcut for simplifying the matrix. However, the problem with Mathematica's shortcuts is that for certain problems, especially in linear programming, it's not going to help you that much. The shortcut is called row reduce. Row reduce, you can look it up, you can read the documentation, you can read I encourage you, please read Mathematica's documentation. Look at the related guides, look at the tutorials, solving linear systems, okay? Mathematica can be a great tool. It can be a great tool. It's a wonderful tool for learning and teaching and doing advanced mathematics. So, take advantage of it. Take advantage of it. The problem with row reduce is that, yes, it will produce this matrix. Okay, however, when you get into certain branches of mathematics, like linear programming or linear optimization, for example, some people call it linear programming, some people call it linear optimization. The row reduce algorithm or the row reduce function in Mathematica is actually going to handicap you. It's not going to help you. So you really need to know Gaussian elimination. You need to understand Gaussian elimination. How would I use this in a course like Calculus 3? Let's take a look. I'm going to go into your Chapter 12 homework, the third Chapter 12 homework assignment. Okay, let's look at, I think the problem is 70 or 71. Let's look at problem 70. Okay, so this this is a good problem too, but we will not be able to use Gauss-Jordan elimination to help solve this problem. Although this is an interesting problem too. Let's look at problem 71. Yes, this is a good example. This is a really, really good example. This is also an example of the Lagrange multiplier method which I will explain in just a minute. Okay? So this is a simple problem in a way, but it covers a lot of different, topics, a lot of different topics. Okay, so let's look at this problem. Number 71 in your third chapter 12 homework assignment. And guys, remember, I cannot do every single homework problem for you. We don't have that kind of time. Okay, I can't spend 24 hours a day making and uploading tutorial videos. Some of this has to be on you. You are responsible for doing the majority of the homework. I can help you with some problems, but I can't help you with every single problem. Okay, we just don't have that kind of time. I certainly don't have that kind of time. And, if I made 100 hours of tutorial videos, would you even have the time to watch all 100 hours of those tutorial videos? Probably not. So it's, that's an unrealistic expectation, okay? However, I will tell you this, if I do a problem for you, there's a very good chance that a similar problem will show up on a quiz or a test. Okay, so please pay attention to these videos. Okay, problem 71 in your third chapter 12 homework assignment. What point on the plane x minus y plus z is equal to 4 is closest to the point x is 1, y is 2, z is 1? Okay, so first of all, if I'm going to start playing around with x, y, and z, I need to clear those variables, right? What is x? X is an integer. What is y? Y is an integer. What is z? Z is an integer. That's not good. Clear x, y, z. Now, what is x? X is a symbol. What is y? Y is a symbol. And what is z? Z is now a symbol. Z is now a symbol. So if I'm going to use Mathematica as a symbolic calculator, that's fine, but I have to make sure that I'm really dealing with symbols, right? Here, x and y and z were assigned integer values. They were no longer symbolic values, okay? So I cleared them. I cleared the definitions of x and y and z. So now x and y and z are back to being symbols rather than numbers, rather than integers. Okay, so let's see. F of x, y, z is equal to x minus y plus z. Okay. And let's start off by checking that this point does not actually belong to the plane. Okay, f of 1, 2, 1 should not be 4, but who knows, maybe it is. And if it is 4, then the answer is simply 1, 2, 1. Okay, so the point 1, 2, 1 does not belong to the plane x minus y plus z is equal to 4. Okay, so now we actually have to do some work. So what is the gradient vector? The gradient vector is simply the vector or the list of partial derivatives. That's all it is. It's the vector of partial derivatives. So for example, for f of x and y and z, okay, what is the derivative with respect to x? It's 1. What is the derivative with respect to y? It's negative 1. What is the derivative with respect to z? It's 1. Okay, so that's the gradient vector for f. That's the vector of the partial derivatives. Very simple. Now here, we have to minimize the distance function. Let me see. Hold on one moment. We have to minimize the distance function. Now, instead of minimizing the distance function, we're going to minimize the square of the distance function because the distance function involves a radical, and that's going to make things more complicated. So to make things easier, we're going to minimize the square of the distance function. But that's fine. If you minimize the square of the distance, you also minimize the distance. So therefore, the distance squared is equal to x minus 1 squared, okay, plus y minus 2 squared plus, my handwriting is usually better than this, but I'm actually writing with my trackpad, my laptop's trackpad, so it's a little bit difficult. Z minus 1 squared. Okay, and the constraint, I'm minimizing this function, and what is the constraint? The constraint is that x minus y plus z is equal to 4. Or some people would say, x minus y plus z minus 4 is equal to 0, and that's fine. You can do that too. Of course, the derivative of a constant is 0, so we don't really, it really doesn't make a difference. Okay, it really isn't going to make a difference. Now, the rule is when you're solving these problems, okay, the rule is this. The gradient vector symbolized by the upside down triangle, the gradient vector of f is equal to some constant. In your textbook, it's called lambda, the Greek letter lambda, times the gradient vector of g. So f is the function that we're trying to minimize, and g, what is g? G is the constraint. The constraint is that whatever values we pick for x, y, and z, it's important that x minus y plus z has to be equal to 4. So the gradient, it's the gradient vector of f, which is the function that we're minimizing, is equal to lambda times the gradient vector of the constraint function. Okay, and let me erase all this because otherwise it's going to be really hard to use Mathematica. So let me erase this. There we go. Okay. So how am I going to do this? Well, think about the equations that I have. Think about the equations that I have. So I'm going to have the derivative of f with respect to x is 1. 1 is equal to, and now think about the derivative. Well, actually, no, sorry about that. Let me start this over. Hold on. So if I have distance, okay. So f, well, I'm making up a new f. Actually, I should call this function g, just to be consistent. So that's kind of, okay, that's a little bit confusing. I should call that function g. Clear f. Okay. G of x, y, and z is equal to x minus y plus z. So for the sake of consistency, I'm going to redefine that. Okay, f of x, y, and z is equal to x minus 1 squared plus y minus 2 squared plus z minus 1 squared. Okay. Okay. So what is the derivative of f with respect to x? Now remember, if you're looking at x, you can ignore, the y's and the z's, okay? So think about this. What happens when you expand x minus 1 squared? If you expand x minus 1 squared, you're going to end up with x minus 1 squared is equal to x squared minus 2x plus 1. So what is the derivative of x squared minus 2x? It's going to be 2x minus 2. It's going to be 2x minus 2. Okay? So we're going to have equation 1 is equal to 2 times x. I'm sorry, did I say 2x minus 1? So the derivative is 2x minus 2. The derivative of x squared minus 2x plus 1 is 2x minus 2. There's stuff going on right now in the kitchen, so I'm a little bit distracted. Making these videos from home it's not easy. There are a lot of distractions at home. So the derivative is 2x minus 1 is equal to lambda escape times 1 times 1. Okay, because that's the derivative with respect to x of x minus y plus z. So this is equation 1. What is equation 2? Okay, well, now expand y minus 2 squared. So that's going to be y squared minus 4y plus 4. So that's going to be, the derivative is 2y minus 4 is equal to the derivative with respect to y of x minus y plus z is negative 1. So that's negative, negative escape lambda, and that's equation 2. Equation 3 is going to be equal to z minus 1 squared. That's going to be z squared minus 2z plus 1. So that's going to be, the derivative is 2z. Oh, you know what? This should be, hold on one second. I'm looking at equation 1. This should be 2. Yeah, sorry about that. The derivative of x squared minus 2x is 2x minus 2. Sorry about that. Okay, my mistake. Equation 3, 2z minus 2 is equal to the derivative with respect to z of x minus y plus z is 1, and then times lambda. And then equation 4 is simply equal to g of x, y, z is equal to 4. And that's it. And if I want to check my derivatives, derivative of, let me see here, derivative of f of x, y, z with respect to x, expand, 2x minus 2, the derivative of f of x, y, z with respect to y, expand, 2y minus 4, and the derivative of f of x, y, z with respect to z, 2z minus 2. Yeah, so my derivatives look fine. Okay, my derivatives are fine. So now I have to solve these equations. Now, I could use the Gaussian elimination, which is fine. There's no problem with that. However, well, I will, you know what, I will use Gaussian elimination. I will use Gaussian elimination. So let's do this. So let me turn on my pen. 1 second. Okay, so I have my X column, my Y column, my Z, my lambda, and my constant. Let's look at the first equation. I have 2 for X, no Y, no Z. I'm going to put lambda on the other side of the equal sign, so that's -1. And then I'm going to put, and remember, there's an equal sign right over here. My constant will be 2. Okay, I'm looking at my second equation, so there's no X. There's a 2Y. There's no Z. There's no Z, and the negative lambda becomes positive lambda on the other side of the equal sign, and then that's going to become a 4. And then I'm looking at my third equation. There's no X, there's no Y. There is a Z, the coefficient is 2. I'm going to put lambda on the other side of the equal sign, so that's negative lambda, so the coefficient is -1. And the -2 is on the other side. I'm going to put that on the other side of the equal sign, so that's going to be a +2. Okay. And then finally, at the very bottom, I'm going to have 1x minus 1y plus z, and there's no lambda, and that's equal to 4. Okay, so let me write this down on a piece of paper, because otherwise I'm going to forget it. Okay, I'm going to write that down. That's my linear system. So 2, 0, 0, -1, 2, that's the top row. And then 0, 2, 0, 1, 4. That's the next row. And then 0, 0, 2, -1, 2. That's the third row. And the fourth row is 1, -1, 1, 0, 4. Okay. Okay, just writing that down on a piece of paper so I don't forget. Okay. Let me make sure that's okay. That looks really good. Okay, let me erase that. Okay, so now clear well, you know, instead of A, I'm going to use B. B is equal to 2, 0, 0, -1, 2, and then 0, 2, 0, 1, 4, and 0, 0, 2, -1, 2, and then 1, -1, 1, 0, 4. Matrix form. Okay. So this should be a 1 up here. That should be a 1. Right? In the upper left corner. Why don't I just switch the first and the fourth rows? Oops. Okay, so I just switched the first and the fourth rows. Now what about that fourth row? I'm changing the fourth row. The fourth row minus 4 times every number in the, or I could just use a space, in the first row. Let's make sure that worked. Oh, because I used -4 instead of -2. Okay, that's a mistake, but that's okay. That's okay. Sorry about that. That was a dumb mistake. It should have been -2, but that's fine. So the fourth row is going to change. The fourth row plus 2 times every corresponding number in the first row. There we go. Okay, so the first column is done. The first column is done. Now let's look at the second column. Second row, that number should be a 1. Okay. How do you change it into a 1? You multiply by 1/2. Multiply by 1/2. Terrific. And now, how do you change that -1 into a 0? So I see here there's a 1, right? So -1 plus 1 is 0. 2. Okay. And now this 2 has to become a 0, right? That 2 has to become a 0. How do you do that? Well, fourth row minus 2 times the second row, because the second row has the canonical 1 in it. Okay, that's looking good so far. I need to change this into a 1. How do I do that? Multiply by 1/2. So I'm changing the third row, 1/2 times the third row. Okay. I need to get rid of this 1 right over here, right? So that's going to be minus the third row, because 1 minus 1 is 0. And then this -2 has to become a 0. Fourth row is equal to the fourth row plus 2 times the third row, because the third row has the canonical 1 there that I need. Okay. And so we're almost finished. So this -3, this is going to have to become +1. How do I do that? Fourth row, -1 over 3 is the reciprocal of -3. Okay. And then to get rid of this 1 here, I simply subtract 1 minus 1, right? There's a 1 here. So the first row, how does the first row change? Every number in the first row minus every corresponding number in the fourth row. And why am I doing that? Because 1 minus 1 is 0. Okay. Second row, how am I changing the second row? Minus 1/2 times the fourth row. And why do I keep on referring to the fourth row? Because the fourth row has the canonical 1 in it. Okay. And then I have one last transformation. I need to get rid of that -1/2, replace it with 0. How do I do that? Well, I'm transforming the third row plus 1/2 times the fourth row. Okay, so now I have that lovely staircase of 1s, and the answers are going to be right over here. So x is going to be 7/3, y is 2/3, z is 7/3. It's not asking for the value of lambda. Lambda is 8/3. So for this problem, we don't have to worry about the value of lambda. I mean, it is important, but it's a value that is often discarded in the very last stage of the problem. Let's see if we're correct. Okay, that's correct. Now, that may seem like a lot of work for one problem, but after doing like 5 or 10 of these, it should be very easy. So again, I realize a lot of you think, oh, Mr. Lewitt, you are such a mean person. You're a mean teacher because you assign so much homework. Well, the bottom line is if you do only 1 or 2 or 3 of these problems, forget it. You're not really going to remember how to do it. I think repetition is an amazing teacher. And the best way to learn something is through constant repetition. I don't care whether you're learning to play the piano, learning to play the violin, learning mathematics, learning how to swim, play basketball, learning a foreign language like German or Spanish or French or Portuguese. Whatever it is that you're learning, you need a lot of repetition. Okay, you need a tremendous amount of repetition, and that's the only way that you're ever really going to learn this material. Okay, you need to just do it a lot. Another good way to learn the material is to actually teach the material to other people. If you work as a teacher, if you work as a tutor, that forces you to learn and relearn the material. Okay, that's another strategy, to get together with your friends and try to teach them as much of the material as possible. By teaching the material to other people, you actually learn the material much better, okay? But again, repetition is very important. It's all about repetition. If you only do a few of these problems, forget it. You really will forget how to do this. But if you do dozens or hundreds of these problems, then it's probably going to stay with you much, much longer. Okay? And some of you really need to know this stuff. If you're going to study data science, statistics, if you want to become an actuary for an insurance company, if you want to become a professional engineer, civil engineer, computer engineer, mechanical engineer, electrical engineer, chemical engineer, anything like that, those people really have to be very good at math. Okay, they have to be very good at math. Okay, so that's it. I think this video has gotten long enough, and hopefully this was helpful to you. Okay, take care and enjoy the rest of your day.